Okay, so today we are talking about significant figures, and you can pause at any point and write down what you see on the screen because these become your notes for this section. So when we record data like you did in the lab last time, either today or yesterday depending on when you were taking these notes, you created what are called significant figures. Even if you didn't call them that, you did. Those are the digits that we can rely on. So, and that becomes important when we want to do calculations from that data. So an example would be if I have, well, let's say that you're at the ball game, you're at the Cardinals game, and you hear them say that there are 38,000 people at the game. Okay, how reliable is that number? Most people would probably guess correctly that 38,000 fans is really only reliable to the nearest 1,000. In other words, only the 3 and the 8 are what we would call significant figures, and these 3 zeros are just placeholders because they need to be there in order for the number to have its true meaning, but it's not a real exact count of how many people are at the ball game. In other words, if you had a giveaway and every fan got a bobblehead or something, you wouldn't necessarily be giving out exactly 38,000 bobbleheads. It might be 37,362 or something like that. It's just a rounded number. It might be a little bit less obvious to sort of determine which digits are reliable with other numbers. So let's say we're doing a lab and you measure out or you see that someone else has recorded a measured value of 5.050 grams. All right. Well, how reliable is that number? If you need to know the exact mass to a certain decimal point, it's important that we understand how reliable the number is that we're looking at. So in this case, it turns out that this number is reliable to that very last zero. It turns out that this number is good to the nearest thousandth of a gram. So how do you know that? Well, I'm going to give you some rules. How do we determine which digits are significant? And again, you're going to want to write this down so you can pause it wherever you need to. The first rule says, and I'm sorry, these are numbered, that all non-zeros are significant. So in the number 12.57 meters, all 4 of those are what we call significant figures. So unlike the example I gave earlier with 38,000 people that had zeros in it, we can definitely rely on all the digits in this number because they're all non-zeros. So in this case, we have 4 significant figures. All 4 of them, the 1, the 2, the 5, and the 7, are significant. Or it might be more important to know how precise the number is. So we might say something like, well, this number has a reliability to the nearest hundredth of a meter because that last significant figure, the 7, is in the hundredths place. All right, so that one has 4 significant figures. All right, the next rule says that captive zeros are significant. So if I have 200,015 pounds, we still would say that the non-zeros are significant, the 2, the 1, and the 5, but we call these guys captive zeros or trapped zeros. And so those would be significant as well because they're surrounded by non-zero digits. Okay, so the other rule, or the next rule for what is significant, these things called trailing zeros are significant. So the rule says if the number contains a decimal, such as the 0 and 2.50, or the last 2 zeros in 0.007200 milligrams, the first, in this case, the first 3 zeros are just placeholders, but the last 2 are significant because they are trailing zeros, meaning that they come to the right of the last non-zero. So let me rewrite this, 0.007200. So our last non-zero is the 2. So everything to the right of that is considered a trailing zero. Trailing zeros are significant if the number contains a decimal. Okay, but the other zeros in there are just placeholders. So this number would have 4 significant figures. Now trailing zeros can be to the left of the decimal point. So I could have, let's say, 310.0, and that would be the 3, the 1, and both zeros would be considered trailing zeros. It's not just this zero after the decimal point that's considered significant. The rule says that as long as it's a trailing zero, and both of those are trailing zeros because they're both to the right of the 1, as long as there's a decimal present, those trailing zeros are significant. It doesn't matter whether they're to the left of the decimal or to the right. So if they're trailing and a decimal is present, they are significant. They're not significant if they're just placeholders. So I already gave you an example of placeholders up above. So these guys in this number are just placeholders because they are not trailing. They are not to the right of the last non-zero. Trailing zeros would be not significant if the number contains no decimal. So in the number 38,000, if the number doesn't have a decimal, which of course people wouldn't be counted with a decimal, but if the number doesn't have a decimal, those are just placeholders. So trailing zeros are significant when there's a decimal in the number. So you have 2 skills you have to learn there. Learn what is a trailing zero, and then also learn, and then also remember that they're significant if the number contains a decimal. Okay, so for this next little part, all I want you to do is in your notes try to answer, underline significant figures in the numbers that I present. And then in your mind, if not on paper, tell why they're significant. So I'll write the number, and then I'll let you think about it, and you can pause the video, and then then I'll tell you the answer. Okay. So let's say we have a measurement 107 miles. See if you can underline, according to the rules that I've given you, the significant figures. Okay, so hopefully you underlined, or you could highlight, that's what I'm going to do, the 1, the 7, and the 0. And the 0 is significant because it's a trailing zero. Let's try the number 0.00504 liters. Which ones are significant? Okay, you should have underlined or highlighted the 5, the 0, and the 4, not the ones to the left of the 5, because those are just placeholders. Remember, they're not trailing zeros because they come before the 5. They're also not captive. This is a point of confusion for a lot of students. The decimal does not make these guys captive zeros. A lot of people think that between the decimal and the 5, those would be captive zeros. They are not captive zeros. To be captive zeros, they have to be between non-zeros, like this 0 right here in the middle of the 5 and the 4. All right, let's try 1,440 seconds. Okay, hopefully you underlined the 1, the 4, and the 4, and did not underline the 0. That is a trailing zero, but since the number does not contain a decimal, it is not significant. All right, let's try 5.09 times 10 to the 7th years. And that number is in scientific notation, but just remember that 10 to the 7th basically just means a 1 with 7 zeros. So that's going to be, what, 50,900,000. Okay, so in scientific notation, and we'll talk a little bit more about scientific notation later, but in scientific notation, the rules we only worry about the coefficient. So this stuff out in front here. And the 5 and the 9 are significant, and the 0 in the middle is captive. The 10 to the 7th just basically represents a bunch of decimal places that or a bunch of places we're going to move that decimal. And so it does not factor in for sig figs. This number would just have 3. Let's try one more. Let's try, this one's a little bit weird, but sometimes you'll see this, 450 written with a decimal milliliters. Okay, so hopefully you said the 4, the 5, and the 0 would be significant. It's kind of rare that you see a decimal with nothing after it, but it is possible that if the ones place is our last significant figure, or in other words, our estimated digit, and it's exactly 0, we would just put a decimal without a 0 following it. And so that follows our rule of trailing zeros are significant if there's a decimal in the number. Okay, the last thing we're going to talk about is rounding your answers when you do math to account for significant figures. So how do we round our answers to show the proper number of significant figures? Because that is important. When you did math in the last lab activity, you had to calculate, I think, a mass, a density, a volume, and you had to use measurements in doing that. So when you use those measurements and you calculate your answer, number one, you want to know where to round it. And then number two, you want to round it properly so that your answer reflects how precise your measurements were. So the rule is, with multiplication and division, your answer should be rounded to the same number of significant figures as the measured value with the fewest. So let's take a look at what that might look like. Let's say I measure the density of something, and density is equal to mass over volume. So that's going to be, if I'm calculating density, I'm going to be doing division, mass divided by volume. So let's say my mass is 432 grams, and my volume is 1.2 liters. So when I do the division, the calculator is going to give me a raw answer. And the calculator gives me a raw answer actually of 360 exactly, and that would be grams per liter. And this answer is actually correct in terms of significant figures. So I'm going to go ahead and circle that or box that in because I don't need to do any more rounding. The reason I don't have to do any more rounding is I took a measured value that had 3 significant figures, 432, and I divided it by a number that had 2. So if the top number has 3 and the bottom number has 2, of course 2 would be the fewest, and so my answer should only have 2. So in this case, the calculator gave me exactly what I needed, 2 significant figures. If I were to throw a decimal on the end of that, that would be wrong because that would give me 3 significant figures. Okay, so let's try another one. Let's move on to addition and subtraction. So in addition and subtraction, when we add up numbers or subtract numbers, our answer can only be as precise as the least precise measured value. So for example, when you were doing your different volumes, it should work out pretty easily when you were doing your volumes for displacement, when you were finding the volume of the stopper. And let's say this is 50 milliliters, and so this is 51, 52, 53, 54, 55. And let's say the little meniscus before you added the stopper was right at 50, and so you correctly recorded 50.0 milliliters because that includes one estimated digit. And let's say after you put the stopper in there, it rose up to, I'm going to call that 53.7. So I have to do subtraction. Okay, and I get 3.7 milliliters. Now in this case, it works out pretty well because if I look at precision, how precise is the number 53.7? Well, it goes to the nearest tenth. How precise is the number 50.0? It also goes to the nearest tenth. So our answer should and does go to the nearest tenth.